All right, let's jump right in. In the world of coding, we are often swimming, if not drowning, in data. And the real challenge, especially when you're in a job interview, is getting answers from that data, like instantly. Today, we're going to master a core skill that'll let you do just that: efficient range queries.
So, picture this. You've got millions of data points, and someone asks you for the sum or minimum of a very specific slice of it, and they need it now. This is exactly the kind of question you'll face under pressure. So, we're going to go on a little journey from the simple, kind of slow methods that just won't cut it, to some seriously powerful data structures that can give you answers in the blink of an eye.
And here's our roadmap for this explainer. We're going to kick things off with the basic problem, then build up our toolkit for different situations, peek at some pro-level techniques, and then wrap it all up with the cheat sheet to make sure this stuff is locked in for your next exam or interview. Okay, so first things first, let's really nail down the problem. What is a range query? And more importantly, why is the first solution you think of, the most obvious one, often our biggest enemy when speed really matters?
You know, the key thing to get here is we're not asking about the entire dataset. Nope, we're zooming in on a specific slice. We're asking questions like, hey, what were our total sales between day 15 and day 45? Or, what was the absolute lowest temperature we recorded during the month of July? It's all about a specific range.
So, the brute force way to do this is dead simple. You just loop through every single element from your start point to your end point and add them up. And yeah, it works, but it is painfully slow. If you have an array with 1 million elements and you get 1,000 of these questions, you're looking at 1 billion operations. In any coding competition, that's a one-way ticket to a time limit exceeded error. It's just not good enough.
So let's level up. What if the data is static? I mean, what if it never ever changes? If we know the values are locked in, we can actually do a little bit of work up front, and that preparation will make our queries unbelievably fast.
Okay, this first idea, it's actually beautifully simple. We just create a second array. And in this new array, every single spot holds the cumulative sum up to that point. It's kind of like the running total you see on a receipt. This pre-calculation step takes O(n) time. But here's the kicker. We only have to do it once. And bam, here's the magic. Once we have our prefix sum array, getting the sum of any range is just one simple subtraction. We take the total sum up to our endpoint, and we subtract the total sum from right before our start point. Just like that. We go from O(n) for every single query down to O(1). That is a huge win.
But here's the catch. That neat little subtraction trick, it only works for sums. It's totally useless for finding a minimum or maximum. For those, we need something else, a sparse table. The idea here is to pre-calculate the answers for all ranges whose lengths are a power of 2, so ranges of size 1, 2, 4, 8, 16, and so on. The setup takes a little longer, O of n log n, but just watch what this lets us do.
Now this is where it gets really clever. It turns out that any range you can possibly think of can be perfectly covered by just 2 of our pre-calculated power of 2 ranges. Yeah, they might overlap in the middle, but for finding a minimum or a maximum, who cares? The result is exactly the same. So after that initial setup, we get our answer in constant O of 1 time. Incredible! Okay, this has all been great, but let's be real. When is data ever truly static? Stock prices change, player scores get updated, inventory levels fluctuate. The second a single value in our data changes, all our prefix sums and sparse tables are instantly wrong. They're totally useless. We need something dynamic. So, let me introduce you to the binary index tree, or Fenwick tree as you'll often hear it called. The best way to think about it is like a supercharged, dynamic version of a prefix sum array. It uses this really clever internal structure based on binary numbers that allows both updates and queries to happen incredibly fast. See, it all comes down to a trade-off, right? With our old prefix sum array, a single update means we have to rebuild the entire thing. That's an O(n) disaster. But the binary index tree, it finds this beautiful balance. Both queries and updates take just O log n time. And that is the absolute sweet spot for dynamic problems where you need to do both of those things all the time. Okay, now for the big one, the Swiss Army knife of range queries. When a problem is really complex or you're just not sure what to use, the segment tree is very often the answer.
The best way to wrap your head around this is to picture a sports tournament bracket. The original numbers in your array, those are the players at the very bottom. Each match combines 2 of them, and the winner, let's say it's the minimum value, advances to the next round. This keeps happening all the way up the tree until the root node, the very top, holds the champion. the minimum of the entire array. So what's so great about it? In one word, versatility. A binary index tree is a specialist. It's fantastic for sums, but a segment tree is a generalist. It can handle almost any operation you can think of, as long as you can combine the results from smaller pieces, so minimum, maximum, even things like the greatest common divisor. You get that same amazing O log n speed for queries and updates. The only trade-off? Yeah, it's a little more complicated to code. Okay, you've got the main tools down. Now, let's level up. We're going to look at 2 professional techniques you'll absolutely need for some of the more advanced problems, especially those where the numbers seem impossibly huge. So, what do you do when a problem gives you these insane numbers, like indices up to 1 billion? You can't make an array that big, but what if you only actually care about, say, 500 of those points? Well, you use index compression. You basically take all those huge sparse coordinates and you map them down to small, friendly numbers like 0, 1, 2, and so on, while keeping their order. This lets you use all our powerful array-based tools on a much smaller, compressed version of the problem.
Now this next one, it's a bit of a mind-bender. It completely flips the problem on its head. What if you need to update an entire range of numbers at once, but you only ever need to ask about the value of a single point? You use a difference array. Updating a whole range from A to B becomes just 2 simple point updates in this new array. And then, finding the value of an element in the original array is just the prefix sum of the difference array, which is a problem we already know how to solve super efficiently.
All right, let's bring it all home. We've covered a lot, so let's get it all organized. If you remember just one thing from this whole explainer for your exam prep, please let it be the decision process that this next slide is going to give you.
This right here, this is your cheat sheet. This is your decision-making matrix. When you see one of these problems in an interview, the very first question you should ask yourself is, will the data be updated? If the answer is no, you're looking at the top half of this chart. If you need sums, it's a prefix sum. For min or max, it's a sparse table. If the answer is yes, the data does update, you're on the bottom half. For simple sums, a binary index tree is your best friend. For anything more complicated, the segment tree is your go-to powerful solution.
And of course, we got to talk about the classic mistakes. These are the little things that can absolutely trip you up in an interview, even if your logic is perfect. Off by 1 errors in your ranges, getting confused between 0-based and 1-based indexing. Pro tip, binary index trees are way easier to code if you use 1-based. These little details are what separate a good answer from a perfect one.
And there you have it, 4 incredibly powerful tools for your toolkit. With these, you can take problems that seemed impossibly slow and turn them into elegant, efficient solutions.
Look, mastering this stuff isn't just about passing a coding interview. It's fundamental. This kind of thinking powers everything from financial data analysis and game development to bioinformatics. The applications are everywhere. You've got the tools. Now go solve some interesting problems.